Hello there guys, and welcome back to another epic inexorable maths video. In this video, we have got quite a long title, Finding the Expected Value of a Function of a Discrete Random Variable. Okay, so we know what the expected value of a discrete random variable is. Okay, it has this formula. So the expected value of x, which is a discrete random variable, is given by the sum over all of the different values of x of the values of x times the probability that the random variable takes that particular value. Okay, so we've already got 2 videos on that. Well, kind of 3 really, if you include my video on the St. Petersburg paradox. The playlist is in the description below. Now we're looking at a function of this random variable, discrete random variable. So what does that mean? Well, it means I don't want to know what the expected value of just x is. I want to know what the expected value of a function of x is, okay? So I'm looking for things like the expected value of sine x, or the expected value, we've kind of already done this, but x squared, or the expected value of 2x plus 10. Okay, so all of these are functions of the random variable. And this is what we're going to look for. Can we come up with a formula, and how do we actually compute it once we've got it? So believe it or not, so in the most general case, we're looking at the expected value of a function of x, and I'm going to call that function g of x because that's pretty common notation. In general, this is what we're looking for. So it's very simple the way that we do it. We just use the same formula as before, and I'm just going to add this straight up. So the expected value of a function of x, g of x, like this, is just the sum over all of the, the function g of x times all of the probabilities of x equaling little x again, okay? That's literally it. So all we've done in this formula is we have replaced the x on its own with g of x. That's it. That's all there is to it. And now, before we go into some really wacky cases like things like sine x and stuff like that, let's look at a very, very common thing that you can deploy and that's very, very useful. So let's look at that right now. Okay, so we're looking at finding the expected value of ax plus b, where a and b are just any real numbers. So maybe instead of the expected value of x, we would like the expected value of 2x plus 1 or something like that. Can we come up with a general formula or an expression using this formula with this? Well, the answer is yes, we absolutely can. So this is how we derive it. And you don't have to derive this every time, of course. Once we've got this in pretty much whatever level of maths you're doing, you can use it without proof, unless the question is to prove it. So the expected value of ax plus b, using the formula, is the sum over all of the values of x of ax plus b times the probability. So the probability, the random variable, is equal to each of these little numbers like this. Now, from here, we can expand it out. So staying inside the sum, we've got ax times the probability that x equals x. So ax times the probability that x equals x. And we're adding, this is all inside of the sum, b times the probability that big X equals little x, like that, close bracket. So all of this is inside of the sum. Now you might be able to see what we can do with this. This is just some basic algebra, really. So what we can do is we can take the a outside of the sum, or actually let's split it into 2 sums first. That's probably a bit better. So let's rewrite this as the sum of ax times the probability that big X equals little x, and then plus the sum of b times the probability that big X equals little x. So now I've written it as 2 separate sums. The reason being, now we can start factoring things like a and b out. So I've just about got space here. Let's take the a out of this one. So we've got a times the sum of x times the probability big X equals little x. That's the first one. And then this one, let's take the b outside. So plus b times the sum of the probabilities of x equaling x, like that. Now, you might be able to see two things. First of all, what we have here is just the expected value of x on its own. Second of all, the sum of all of the probabilities over every value of x is definitionally the number 1, because in any situation involving a random variable, the sum of all of the probabilities are going to be the number 1, right? So this whole sum here is always the number 1, okay? And we can do a bit with that. I'm gonna go over here to finish this off. So the whole thing, both sums, we've got a times the expected value of x plus b times the number 1. Okay, cool. So now we've got a nice little formula. It turns out the expected value of any number times x plus any other number, ax plus b, can be simplified to just a times the expected value of x plus b. So what I'm saying is, if you know the probability distribution of x and they ask you to find the expected value of, I don't know, 2x plus 1, you can just get the expected value of x normally, and you can just, you know, whatever the values are, if that's a 2 and that's a 1, it's just 2 times the expected value of x plus 1, or whatever it might be. So this is really, really handy. It's not always the case. We're not going to be able to do this with stuff like sine x or whatever, but for what you would call a linear combination of x's, or a linear function of x like this, ax plus b, that is what we've got. Very nice formula there that we'll use in a second. Guys, so here is a question. The random variable x has distribution here. So there's x, there's the probability that the random variable is equal to each of those values of x. Find the expected value of 2x minus 3. Okay, so how are we going to do that? Well, if you wanted to, you could work out, what, you know, for each value of x, what is 2x minus 3, do the probabilities like that. A little bit annoying, a little bit boring. So we're not going to do that. We're going to do using the formula that we've just derived. So first of all, let's work out what the expected value of just x is, and then we can just times it by 2 and then take away 3. That's basically all we're going to do. So remember from the previous videos, or just any of your previous knowledge, the expected value of x, and also it's right there, is equal to just each of these columns multiplied together and then added up. So 1 times 0.1 is 0.1, plus 2 times 0.3, that's going to be 0.6. 3 times 0.2 is also 0.6. And finally, 4 times 0.4 is 1.6. We're going to add these up. So we've got 0.6 plus 0.6, that's 1.2. Add another 0.1, that's 1.3. Plus 1.6, that's going to be 2.9. So the expected value of just x is 2.9. But what we're going to do is multiply that number by 2 and then take away 3. Because the expected value of whatever this is, 2x minus 3, is 2 times the expected value of x and then minus 3. It's that simple. So the expected value of 2x minus 3 is just going to be 2 times 2.9 minus 3, like that. So that number, 2 times 2.9 minus 3, is just, of course, going to be 2.8. So this is equal to 2.8. And that is the answer to the question. Okay, now let's go and look at some more crazier functions, not just linear functions, some crazy stuff, and see what happens. Okay, so the random variable x has distribution given there. The first part of the question is simply to find the expected value of x, so nothing too crazy at all. So let's actually find that. So again, the way that we're going to do this is the same as always. So the expected value of x is 1 times 0.4 plus 2 times 0.2, so 0.8, or 0.4, sorry, my mental maths. 3 times 0.1 is 0.3, and then 4 times 0.3 is 1.2. And so this is 0.4 plus 0.4, so that's 0.8, plus 0.3, 1.2, so that's 1.5. So that's 2.3 overall. So the expected value of x is 2.3, and it is that simple. Now, let's ramp it up a little bit. What about the expected value of the square root of x? So the second part of this is to find the expected value of the square root of x, okay? So how are we going to do that? Well, all we are going to do is use the formula. That should be a capital X. We're just going to use the formula. Now, what I will do here is I'm going to directly write it down in the most specific notation possible because it's going to help us out later. Okay, so just if you're wondering why am I choosing to write this like how I am, this is going to be useful for another question later on. So the way that we do this is we say this is equal to the sum of the square root of x times the probability that x is equal to x. So that's nothing new. But what I am going to do for this specific question is actually write down which values of x are we summing over. So this is from x equaling 1 up to 4 in this question, okay? So this is going to come up later. You might say, why are you being so specific right now? Even though this is what we've always been doing, it's going to come up later. So you can do this one for yourself, or I'll write out, I won't do all the working out for it because that'll be a bit too long, but I'll write down the actual, like how you start it, and then I'll just tell you what the answer is just to save a bit of time. But what we do is we take the square root of each value of x and times it by its probability and then add them all up. So the square root of 1 times its probability, 0.4. And then we add the square root of 2 times its probability, which is 0.2. Then we add the square root of 3 times it by its probability, which is 0.1. And then finally, we add the square root of 4 times its probability, which is 0.3. Okay, so that's what you get there. Have a look at that and make sure that you are happy with it. It ends up being 1 plus root 2 over 5 plus root 3 over 10. Those are all separate things, 1 plus root 2 over 5 plus root 3 over 10, or if you prefer it as a decimal, which I personally do, it's approximately 1.456, okay? So it's roughly speaking 1.456, okay? Just to save time, basically that one you would just plug into a calculator because it's an irrational number because we've got root 2s and root 3s in there. Okay, so same question, let me actually rub off the board. So same question again, the same context, the same setup of the question, but the third part is to find the expected value of 2 to the power of minus x, okay? So the expected value of 2 to the power of minus x, feel free to pause the video and give it a go if you like, would be the sum over, again, the same x values, 1 to 4, of 2 to the power of minus x times each probability that x equals that number, okay? And again, I'm being a bit more specific now because it's going to come up later. And so again, we can just do this manually kind of, so just plugging everything in. So 2 to the power of minus 1 times 0.4 plus 2 to the power of minus 2 times 0.2 plus 2 to the power of minus 3 times 0.1 and finally plus 2 to the minus 4 times 0.3. And again, for this one, I'm just going to save you guys the time because otherwise it's just, you know, a little bit long and boring and stuff. But we end up getting 0.28125. 0.28125. Feel free to check that for yourself if you like, but that is the answer to that one, okay? Now, I keep building up to this like, oh, it's going to save us later. Now, I'm going to show you a question that it's very, very useful to have written this in the proper sigma notation. Let's have a look at it. So the random variable x has probability mass function defined by this probability. The probability that the random variable is equal to little x is 2 times 3 to the power of minus little x. And this is defined for every single positive whole number, 1, 2, 3, 4, 5, all the way up to a million or a billion or a trillion, as far as you want to go, all the way to infinity, okay? Every single natural number. And we're being asked to find the expected value of 9 to the power of minus x. So there's quite a lot going on here, and we're actually going to use the sigma notation stuff, and that's why we've been writing it out properly, because, as you can see, we can't do infinitely many calculations here, because we can't really use this formula indirectly, because then we'd be doing infinitely many columns, right? I'm not going to write out the whole table for this because that's infinitely many columns. So we need to use some sigma notation, and maybe it's going to involve some standard formulae that you may know from like pure maths. So let's have a look. First of all, let's just verify that this actually is a probability distribution, because it's not that obvious. Now, what do I mean by that? How do we verify that something is a valid probability distribution? Well, first of all of the numbers need to be positive. All of the probabilities need to be positive, that is. So we've got that, right? These are all positive numbers. And second of all, the sum needs to exactly add up to 1. So let's just check this, right? We're just checking. So the sum of all of the probabilities, so 2 times 3 to the minus x, and this is from x equals 1 to infinity. Does this actually add up to the number 1? Well, this is where the pure maths comes in. So this, guys, is actually going to represent a geometric series, and that's how we can check it very quickly, okay? So if you're not happy with geometric series, this question might not be for you, because it's going to come up this right now and in a minute as well. But what do we do here? So this is a geometric series. If you don't believe me, start writing out some terms from it. You'll see that it definitely is. What's the first term in the series? Well, it's 2 times 3 to the minus 1. So that's 2/3, okay? So do you know what? I'll start writing out a few terms. The next term here is 2 times 3 to the minus 2. So that's 2/9. 2/9. The next term is 2 times 3 to the minus 3. So that's 2/27. And that goes on forever, okay? So you might remember from geometric series, if that's a topic that you've done before, it probably is, you might know that the sum to infinity, S infinity, normally written, is equal to the first term, normally U1 or maybe A, divided by 1 minus the common ratio, okay? We need to make sure that this is equal to exactly the number 1, because it's a probability distribution. So all of the probabilities must add up to the number 1. So this is equal to the first term, which is 2/3, divided by 1 minus the common ratio. And the common ratio here is 1/3, because you can see to get from one term to the next, we're timesing by 1/3. So this is our fraction. You could chuck it into a calculator if you really want, or we could just times the top and the bottom of the main fraction by the number 3. We end up getting 2/3 minus 1, which is 2/2, which is 1. That means that every probability here adds up to 1 in total, which is exactly what we wanted. So we know, before actually starting the question didn't ask us to do that, but we know that this is definitely a valid probability distribution, okay? Cool, now let's actually get on with the real question. Okay guys, so now that we have verified for sure that this is a valid probability function, we can now look at finding the expected value of 9 to the minus x, which is the actual question that's being asked of us. So just simply using the formula, and this is why it's so important I've been emphasizing to use that sigma notation, we can rewrite this expected value using this guy here. Okay, the expected value of g of x is given by that sum. So g of x is 9 to the minus x. And in this case, the probability also has a very nice expression. It's 2 times 3 to the minus x. So I'm going to write this as 2 times 3 to the minus x, okay? And it's very important to write down what we're actually summing over. And we can see here we're going from 1 to infinity, okay, like that. Now, the objective is to use probably geometric series to work out what this is equal to. So first thing I'm going to do is take the 2 to the outside of the sum, because it's just getting in the way. Okay, the next thing I'm going to do is rewrite it. So x equals 1 to infinity. And I'm going to notice that actually 9 is already a power of 3, right? 9 is 3 squared. So I'm going to rewrite 9 as 3 to the minus 2x there, and then times it by 3 to the minus x, because that was already there. So I'm rewriting 9 as 3 squared. Hopefully this makes sense. It's not too much of a jump. 9 is 3 squared. So 9 to the minus x is 3 squared to the minus x. This is what I've done. And then that's 3 to the minus 2x, because you times these together. That's what I've done, just to be really clear on that. Okay, cool. Now we can add the powers together for the 3 to the minus 2x and 3 to the minus x. So this is equal to 2 times the sum from x equals 1 to infinity of 3 to the power of minus 3x. Okay, just adding those together, minus 2x plus minus x, that's minus 3x. And guys, it's going to actually transcend that this is, again, a geometric series. And just to really show it to you here, we can rewrite this one more time as 2 times the sum from x equals 1 to infinity, and then 3 to the 3, or 3 to the minus 3, is the number 1 over 27. So this is basically 1 over 27 to the power of x. Or you could have 27 to the power of minus x. That's fine, that's the same thing. And now we can clearly see, if I was to write some terms out of this, the first term is 1 over 27. The next term is 1 over 27 squared. And this definitely is a geometric series, isn't it? Because we're getting this pattern and that goes to infinity. Okay. So again, using the sum to infinity formula, I'll just about got space here to squeeze it in. Using the sum to infinity formula, the first term here, I'm going to ignore the 2 for now. The first term is 1 over 27. So 1 over 27. And we're dividing by 1 minus, and the common ratio is also 1 over 27. There we go. And then let's put that 2 that's in front of it back in. So there's a big 2 there. So we've got 2. And then inside of this fraction, if we times the top and bottom by 27, we get 1 over 27 minus 1. And this ends up simplifying to 2 over 26 overall. Okay. And then that ends up being 1 over 13. So what that means is, for this fairly complicated question, the probability with a probability function there, probability mass function is just the same thing as this is the probability the random variable is equal to this number and this number and this number. Nothing new, just a more technical term. The probability mass function being this implies the expected value of 9 to the minus x is 1 over 13. Very cool question, quite difficult. We used a lot of different areas of maths. If you managed to stick around this long, I thank you very much. And also I applaud you, because not an easy question at all. Please stick around for future probability videos coming at you very shortly. Public service announcement, you'll never, ever see a mid-roll ad on this YouTube channel in your life. If you do, leave a comment on the video and I will delete it. I do not believe that it's right to be watching adverts in the middle of a YouTube video that's especially based on education. It's really annoying and it's terrible and I don't endorse it at all. So if you ever see a mid-roll ad on this video, let me know, I'll delete it, but there shouldn't be any on there. So there you go. Thank you so much for watching. As always, I highly appreciate it and I'll see you in the next one. Cheers.